In this video, we're going to have a think about lenses and we're going to figure out how it's possible to predict the kind of images that they produce. In this video, we're going to concern ourselves with what we call a convex lens. Now, a convex lens is one of the lenses that curves outwards, as opposed to a concave lens which curves inwards. Convex lenses are also known sometimes as converging lenses, and we'll see why. So to converge means it brings light to a certain point. So we're going to draw the lens here. When we draw the lens, we only really need to draw it as a line. And what I want to draw now is, to illustrate the idea that it converges, is I'm going to draw three rays of parallel light. Now, parallel light has a special significance in this topic in that it represents light from infinity, but it's nothing you need to worry about just at the moment. So we've got three parallel rays of light going into the lens like that. Now, what happens with this kind of lens is that these three rays of parallel light will all converge, hence the name converging lens. They will all converge at the same point. And that point is given a special name. That point is referred to as the principal focus. The length from the lens to that point is often referred to as the focal length. So the focal length would be the distance from the lens to the point where they have converged. And that is often written with the symbol F. Now, this focal length is very important, and when we're drawing diagrams for lenses, we often just think in terms of the focal length. You see, different lenses will have different focal lengths. Some lenses may have a focal length of 10 centimeters, some might be 15 centimeters, some might be a meter. So what we do is when we draw diagrams, we draw the lens, as you can see there, as a vertical line. Then we draw this line through the middle, which we're going to call the principal axis. And that's the line that goes through the middle. And then we're going to label this diagram with distances, but we're going to do it in terms of F, or focal length. So this would represent 1F. Over here, I have to keep the scale the same. This would be 2F. This one over here would be 3F, and so on. Now, behind the lens, we can do the same sort of thing. This one I'm going to call minus F, or you could call it perhaps F dash. Over here, we can move another one there, and we can call that one minus 2F, or we could call it 2F dash, and so on. Now, when you do these diagrams yourself, it's important to keep the scale correct, otherwise the whole thing will go wrong. So we draw it like so. Now, these diagrams will actually help us predict what kind of image will be formed and where, depending on where we put the object. So what we do is we imagine that we place an object at a certain place. So let's, just for sake of argument, let's place an object at about minus 3F here. So we usually draw the object, we draw it as a line, and then we can do some sort of blob at the top there. And that object could be a light, could be something giving out light, or it could be something reflecting light. The point is that we can draw some rays of light coming from it. And what we do is we draw three rays of light. Now, of course, there's an infinite number of rays of light coming from it, but we're just going to choose three. We always do one parallel to the principal axis. So that's the first one we do, is parallel to the principal axis. And what we're going to do is we're going to create a set of rules around these in a moment. Parallel to the principal axis. The second one we draw is one that passes to the exact center of the lens like that. So the second one that we do there is to the center of the lens. And then the third one that we draw is a light that passes through F dash. So one that passes through F dash, negative F dash, sorry, on this side there. So the next one, the last rule there, is it passes through negative F or F dash, whatever you want to call that one. For each of these, we have to apply a rule. So let's do them in turn. So for the ray of light that was parallel to the principal axis, well, this one always comes out through the lens and passes through F, passes through the principal focus at 1F there. The one that goes through the center of the lens, well, this one always passes through the lens and is unchanged. We say is undeviated as it passes through. So what that looks like in practice will be something like this. Something like that there, okay? So we can see that it's passed through the lens and it did not change direction as it passed through the lens. That's the second rule. Now, you only actually really need these two rules, but we usually check that we've done everything correct by applying a third rule. And the third rule is the one that passes through negative F or F dash. And that one always emerges parallel to the principal axis and comes out like so. And if we've done our diagram correctly, we should find that they all meet at the same place. This place gives us the size, the orientation, and the type of image that has been produced. Let's make a note of these rules, and then we'll come back to what the image looks like. So the one that was parallel to the principal axis always goes through F, the principal focus. The one that was through the center of the lens is undeviated. And the one that passes through negative F or F dash emerges parallel to the principal axis. And they should all meet at the same place, remember. And that place is where we say the image is formed. So let's go back to our image over here and let's see what we can learn about our image. Well, we can learn about the size of the image. It's definitely not magnified. It's not the same size. This one would be classed as, we would say, it's diminished. It's smaller. And you could measure it. You could literally measure it and you could work out the magnification. It's diminished. We also can see that it's upside down. So we can see that the image there is upside down. You may have noticed that when you do that with lenses, sometimes you get an upside down image. In this case, we get an upside down image. Now, we can also learn the position. Now, it looks to me that it was formed somewhere here, which is, it's hard to tell on this scale, but somewhere between F and 2F. So why don't we just say the image is formed at 1.5 F. Again, if you knew how many centimeters each F was, you'd be able to figure that out in centimeters. And what it also tells us is that the image that's been produced is a real image. Now, real images are always formed on the right-hand side of these diagrams. If the image was formed on the left-hand side, it would be called a virtual image. A lot of people struggle to see how a virtual image could be produced. So let's have a look at that one. Let's see what happens when we place the object somewhere else. So what I've done here is I've placed the object, which is here. Remember, it's the line with a sort of blob at the end there. So we've placed that one somewhere between minus F and the lens. So I don't know, could be minus 0.5, minus 0.6 F. Let's apply the rules and see what happens in this really quite special case. So we do the first rule, which of course is the line which goes parallel to the principal axis. And we know that that line must pass through F. So we can draw it like that. So there's the first rule. Now the second rule was about the one that goes through the center of the lens. So let's try that one. So if we draw a line that goes through the center of the lens, and we can see it like so. Now there's a problem here, or there seems to be a problem, because these two lines are not going to meet each other. Last time, if you remember, they met over on the right-hand side. This time they cannot do that. So it causes a problem. There's also another problem. If we want to apply the third rule, and the third rule we said was one that goes through minus F, well, if we do draw a ray of light that goes through minus F, well, that one doesn't even hit the lens. So this is definitely a different story. We can only use the first two rules, but they still don't seem to work. Well, this is where we have to have a leap of imagination here. We have to imagine that there is somebody over here watching it. That's an eye. Somebody is watching it here. Now, what the human brain does, the human brain believes that light travels in a straight line, and so it will follow these rays back to an imaginary point. So what your brain will do is it will follow the path of this ray of light and believe that it's coming from somewhere over there. And we can do the same with this one. This will also be followed back by your brain, and you will see that they kind of meet at a point around about here. Well, at this point, this is where your image is going to be formed. So it's quite different than the previous example. The image is now here. Now let's write down what we know about this image. Unlike the previous one, this one is upright, it's not upside down. Also, it's magnified. And you could calculate the magnification by literally just counting the number of squares. It's magnified. It's formed at, I don't know, what should we say, about minus 1.3, 1.4, 1.5 f. Anyway, we can say its position. Let's just call it, let's say, at 1.4 f. But what is more significant is the type of image. If you remember, real images get formed on this side, which means the one that we've just formed over here must be a virtual image. It actually doesn't really exist. Your eyes and your brain believe there is something there. This would be equivalent to you using a magnifying lens. You bring the object close, you see an enlarged version of the object and it's upright. Actually, what's happening is when you brought the object close, you were bringing it closer than negative f, and as a result, a virtual image was created which was magnified and was upright.